Welcome to G Fun Facts Online. Our planet, a vibrant oasis of life, bears the indelible marks of a tumultuous and violent past. Long before humanity, Earth was a target in a cosmic shooting gallery. Giant asteroids and comets frequently collided with our world, unleashing planet-shaping events of unimaginable power. These ancient impacts are not just geological curiosities. They are profound testaments to the forces that have sculpted our planet's history, from its geological framework to the intricate tapestry of life itself. Today, we're conducting a forensic investigation into these enduring scars, cataclysms that, in their destructive fury, paved the way for the world we know today. For much of human history, the idea that mountain-sized rocks could fall from the sky was considered fantasy. It wasn't until the 19th and 20th centuries that scientists learned to read the subtle clues left behind by these colossal collisions. Unlike the Moon, whose pockmarked face is a pristine record of bombardment, Earth is a dynamic planet. Erosion, tectonic plate movement, and volcanism work tirelessly to erase or bury the evidence. This makes the hunt for ancient craters, or astroblems, a true detective story. The most definitive proof lies in the rocks themselves. The immense pressures and temperatures from a hypervelocity impact create unique changes in minerals, a phenomenon called shock metamorphism. One of the most telling indicators is shocked quartz. Under the intense pressure, the crystal lattice of a quartz grain is deformed, creating microscopic parallel lines known as planar deformation features, or PDFs. These are considered unambiguous evidence of an impact, as no known earthly process, like a volcanic eruption, can create them. Similarly, finding high-pressure minerals like coesite and stishovite near the surface is another strong clue. Another crucial piece of evidence is the presence of shatter cones. These are distinctively conical fracture patterns that form in rocks hit by an impact shockwave. Their apexes point towards the direction of the impact, acting like a cosmic compass pointing to ground zero. The discovery of shatter cones in the mid-20th century was pivotal, helping to confirm the impact origin of structures like the Vredefort Dome in South Africa, which was previously mistaken for a volcanic feature. For many of the largest impacts, the original crater is long gone, buried or eroded away. Here, scientists use geophysical surveys to see beneath the surface. Gravity surveys can detect anomalies in Earth's gravitational field caused by the lower density, fractured rock within a crater. Magnetic surveys can identify variations in the magnetic properties of rocks that were altered by intense heat. Seismic reflection surveys, which send sound waves into the ground and measure their reflections, are especially good at imaging the complex, multi-ring structures of large buried craters like Chicxulub. Finally, the chemical signature of the impactor itself can be the smoking gun. The discovery of a thin, global layer of clay at the boundary between the Cretaceous and Paleogene periods was a breakthrough. This layer is enriched with the element iridium, which is rare in Earth's crust but abundant in asteroids. This iridium layer is the damning evidence linking the demise of the dinosaurs to a massive asteroid impact 66 million years ago. With these tools, scientists have identified over 200 impact structures on Earth. Let's take a tour of some of the most significant. First, we visit the Vredefort Dome in South Africa. This is the central uplift of what was once the largest and oldest known impact structure on Earth. Dating back an astonishing 2.023 billion years, the original crater is estimated to have been up to 300 kilometers, or 190 miles, in diameter. The impactor, a colossal asteroid between 10 and 25 kilometers wide, slammed into the planet with an energy that dwarfs any other known event. The Vredefort Dome we see today, a ring of hills about 70 kilometers across, is the deeply eroded remnant of the ground that rebounded upwards in the seconds after impact. Next, we travel to Ontario, Canada, to the Sudbury Basin. This is the remnant of a massive impact that occurred around 1.85 billion years ago. The original crater was likely 200 to 250 kilometers wide. The impact was so powerful, it's thought to have punctured Earth's crust, allowing magma from the mantle to well up and fill the basin. This molten rock was rich in heavy metals. As it cooled, it created one of the world's most significant deposits of nickel, copper, and platinum group elements. Here, a cosmic cataclysm became the foundation of a thriving industrial region. Of course, no tour is complete without visiting the most famous crater of all, Chicxulub, buried beneath Mexico's Yucatan Peninsula and the Gulf of Mexico. This 180-kilometer-wide crater is the scar left by the asteroid that led to the mass extinction of the non-avian dinosaurs, and about 75% of all species on the planet 66 million years ago. The 10 to 15-kilometer-wide asteroid slammed into a shallow sea, vaporizing vast amounts of water and sulfur-rich rock. The immediate aftermath was a hellscape of mega tsunamis, global wildfires ignited by re-entering debris, and a blast wave that flattened everything for hundreds of kilometers. Beyond these giants, other craters tell fascinating stories. The Manicouagan crater in Quebec is a distinctive 214-million-year-old ring-shaped lake, easily visible from space. In Arizona, the 50,000-year-old meteor crater is so well preserved it was used for astronaut training. And the entire Chesapeake Bay in the United States is the result of a 35-million-year-old impact that still influences the region's geology today. So what exactly happens in the moment of one of these collisions? It's an event of almost unimaginable violence, unleashing a symphony of destruction. The kinetic energy of an object several kilometers wide traveling at tens of thousands of kilometers per hour is equivalent to millions of the most powerful nuclear bombs ever created. Upon impact, a powerful shockwave propagates into the asteroid and the Earth's crust, generating pressures so extreme they can vaporize the impactor and a significant portion of the target rock almost instantly. This creates a rapidly expanding plume of superheated vapor and molten rock ejected high into the atmosphere. Simultaneously, the shockwave expands outwards, compressing and fracturing the bedrock. As the shockwave passes, the compressed rock rebounds, creating a central uplift in large craters. In the moments following, a transient crater is formed, which then collapses under gravity to form the final, wider, shallower structure. Vast quantities of ejected material, or ejecta, are thrown out, blanketing the surrounding landscape for thousands of kilometers. But the destructive fury doesn't end there. The long-term consequences can be even more profound, altering geology, climate, and life on a global scale. One of the most significant effects is a drastic change in climate. The vast quantities of dust, soot from wildfires, and sulfate aerosols ejected into the stratosphere can block sunlight for months or even years. This leads to an impact winter. With sunlight unable to reach the surface, global temperatures plummet, and photosynthesis grinds to a halt, causing the collapse of food chains and widespread extinctions. This is precisely what followed the Chicxulub impact. The planet's chemistry is also profoundly altered. If the impact strikes sulfur-rich rocks, like the gypsum at the Chicxulub site, vast amounts of sulfur dioxide are released, leading to devastating sulfuric acid rain. The high temperatures can also cause atmospheric nitrogen and oxygen to combine, forming nitric acid, further poisoning the world. On a geological timescale, large impacts can have a lasting effect on the Earth's crust. They create deep fractures and can trigger extensive volcanism and hydrothermal activity. The Sudbury impact is the prime example, where the breach in the crust led to the influx of metal-rich magma that formed its valuable ore deposits. But here's where the story takes a fascinating and counterintuitive turn. Amidst all this destruction, impacts may have played a critical role as a cradle for life and evolution. One leading theory for the origin of life is that essential organic molecules, like amino acids, were delivered to Earth from space by asteroids and comets. The period of intense bombardment early in Earth's history could have seeded the young planet with these vital ingredients. The craters themselves may have then provided the perfect environments for life to take hold. The impact process creates extensive fracture networks and generates long-lasting hydrothermal systems. These warm, mineral-rich vents, shielded from the harsh surface conditions of the early Earth, are considered prime candidates for the origin of life. The very events that made the surface uninhabitable could have simultaneously created ideal subterranean incubators for life. Finally, mass extinction events, while devastating, are powerful drivers of evolution. By wiping out dominant species, they create ecological vacuums that allow other species to diversify. The extinction of the dinosaurs is the classic example. Their demise cleared the way for the rise of mammals, which had been small and largely nocturnal for millions of years. Without the Chicxulub impact, it is highly unlikely that humans would be here today. The enduring scars of ancient asteroid impacts are far more than blemishes on our planet's surface. They are fundamental to Earth's story. They have shaped our geology, created vast mineral wealth, altered our climate, and, in a remarkable paradox, may have helped spark life and then driven its evolution. The study of these ancient impacts is a constant reminder of our planet's place in a dynamic cosmos. The echoes of these ancient collisions reverberate through geological time, a powerful testament to the resilience of our planet and the intricate, often violent, dance of creation and destruction that defines the universe.